Hello, welcome to Chapter 0 of the Finite Element class at Universidad de los Andes in Chile. In this chapter, we're going to be talking about introductory subject into the finite element class, that is the direct stiffness method. Now, the direct stiffness method, as we will formulate and see in these slides, is what we will be using throughout the course to assemble our stiffness equations, irrespective of what the problem we're dealing with. That is, if it's elasticity, if it's a thermal problem, whatever it is, we're always assembling our equations using the direct stiffness method. So to set up a simple problem we can use to illustrate what the direct stiffness method does, we will use this little truss problem. The idea here is that we have a truss and we want to find the cross-section area of all members. We will assume they're all the same, such that the midpoint vertical deflection, that is this point over here, is 2 centimeters. And we are given a force of 100 kilonewtons. We have all members are 5 meters, that is, we have a truss that is made up of equilateral triangles. And we will figure out what the displacement is, and based on that, we will iterate over the cross-section area until we get 2 centimeters. So in this moment, we will set up what a typical problem setup is. We start by numbering our nodes. So that is, we need to specify the points at where our structure is connected. In this case, we have a structure made up of truss bars, which connect 2 nodes. So we're going to start with an index of 0 because we'll be using Python to implement this. So we have a table of nodes which consists of a node number, basically an index to the coordinates of the nodes, and the x and y coordinates of the nodes. This is our table of nodes. Next, we need to specify our table of element connectivity. That is, we need to number our elements, and we'll have a number of element, and then we'll have integers specifying what nodes are connected by that element. So for example, element number 0 here, it connects nodes 0 and 1, and so on. Element number 4 over here connects nodes 1 and 4, right? So element k in general connects nodes ni and nj. And then we need to specify boundary conditions. So in this case, we have a simple fixed support at node 0, and we have a sliding support in the x direction at node 2. And we're going to use this format to specify fixities. We'll have a column of node number, and we'll specify the degree of freedom that is constrained. So in this case, if we constrain the x degree of freedom, that is degree of freedom number 0, and so on. Degree of freedom 1 at node 0 is going to be the vertical degree of freedom, and degree of freedom 1 at the number 2 node is going to be the vertical degree of freedom there. Optionally, we can have a DOF value, so a value for our solution. We'll set those to 0 for now, but we'll see that the direct stiffness method allows us to have values of the degrees of freedom which we are trying to fix. Then we'll have a similar table for the applied loads. The table consists of a node number column, a loaded degree of freedom column. In this case, since the load is vertical, we'll have a load in the y direction, that is direction number 1. Remember that directions and all indices start from 0, so 0 is x, 1 is y, and in 3D we would have the z direction be direct DOF number 2. In this case, we use a negative value because the load is pointing downwards with 100 kilonewtons. And that concludes our setup of the problem. Next, we need to think about the degree of freedom numbering. In this case, we're going to be using a simple numbering scheme where we associate 2 degrees of freedom, 2 displacement degrees of freedom at each node. So we have u0 in the x direction, u1 in the y direction, and in general, we're going to have a simple rule, in this case a numbering rule for the degrees of freedom, and this is going to tell us where in our stiffness equations to add the contributions of each element. So at node n, in general, we will define the degrees of freedom u2n and u2n plus 1. For this case, where we have 2 degrees of freedom per node. If the problem changes, we might have 3 degrees of freedom per node, 6 degrees of freedom per node, 7, And in this case, the numbering rule will change. So you need to be aware that this rule is just specific for the truss problem. So once we have numbered our degrees of freedoms, we collect them all visually into one degree of freedom vector, U0 all the way through U9. And then the next step is to form the stiffness equation. So we need to form the system K with the stiffness matrix times the degree of freedom matrix is equal to the external forces. So in order to do that, we will need to do stiffness assembly, and this is what the direct stiffness method does. So let's say, for example, element 3, we pick element 3. Element 3 connects nodes 1 and 3. And at nodes 1, I have degrees of freedom 2 in the x direction, 3 in the y direction, and at node 3, we have a degree of freedom 6 in the x direction and 7 in the y direction. That means my local degree of freedom vector, so local to this element, corresponds to the subset of the global degrees of freedom, just U2, U3, U6, and U7. These belong into the global stiffness equations too, but they're also local to this element. And for now, we'll just think about the element stiffness as a known thing. You can see the other video I prepared talking about the stiffness of the truss element, if you want to see where that comes from. But for now, we'll have it as a given. So if we know the element stiffness and the right-hand side vector from the element information, we can assemble the stiffness equations for this element, and we can see the contributions to the global stiffness. For now, the weight of the element, we'll just assume that it's half the weight at each node in the vertical direction, and that's going to be our F right-hand side. So we have this known stiffness equation, which we can basically partition our element stiffness in this way. So we have the displacement. So note that this is a vector right here. So this is a 4x4 matrix. So these are the displacements at node 1, that is U2 and U3, and these are the displacements at node 3, which are U6 and U7. If we take this in this form, we can partition the matrix in this way. These are the components of the stiffness matrix that correspond to node 1, and these are the ones that correspond to node 3, and these are the coupling terms. The same for the right-hand side. Now, if we have the global stiffness equation in this way, so basically we want to see for all the nodes of the system, so we have nodes 0, 1, 2, 3, and 4, the contributions of each sub block of the element local stiffness goes to the block that corresponds to that particular node. So this 2x2 matrix will go to the 2x2 matrix submatrix that corresponds to node 1. The 1, 3 matrix, this one will go to the 1 and 3. And if there's something there beforehand, maybe a contribution from element, this element that is diagonal bar over there. So in that case, maybe in that case we will add whatever is there. So that's what this little plus means. It means we add all the element contributions. So in that way, if we see another element, for example, element 4 connects nodes 1 and 4. So we're going to take a look at the columns and rows of the matrix that correspond to nodes 1 and 4, and just form the stiffness matrix for the little element we're talking about, and just add the contributions of these elements to those rows and columns of the stiffness matrix. And the right-hand side go to the right-hand side with a similar idea. So if you want to speak of an algorithm, we will think of the stiffness assembly process as a loop over the elements, where for each element E, so we're standing in some particular element, we will form its element stiffness matrix and force vector. And that usually comes from element properties such as modulus of elasticity, maybe Poisson's ratio, and density, for example, and also information about what nodes are being connected. So for example, from the connectivity of the element, I can get the length of the element, and that'll go into the stiffness calculation. So I can form this local element stiffness equation, and we get the nodes that it's connected to, Ni and Nj, and we define this vector of local degrees of freedom. So the mapping of the element degrees of freedoms from local degrees of freedom to the global, right? So the 0 element of the stiffness equation, the 0 DOF, will correspond to the global 2ni DOF, degree of freedom. And we just add the contribution of this element into global stiffness equations, which might be written in pseudo Python code in this way. So given that we have this definition of what the local degrees of freedom are, we just span the I and j column of the K matrix. So that's this n DOF per node is going to be, in this case, each node has 2 degrees of freedom. So I in range n DOF per element. Actually, this one is 4. So we will see that at the PQ position of the K matrix, we add the IJ position of the K matrix, where P and Q are indices IJ into this degree of freedom matrix locally. So basically, this is what you need to implement the direct stiffness method in finite elements. And this same algorithm is useful for any problem, actually. Then regarding the nodal loads, we have a similar situation where we can have, in this case, we're looking at the blue arrows are the degrees of freedom, and the red arrows are the forces corresponding to each degree of freedom. So what we want to say here is that only at node 4 in the vertical direction we have 100 kilonewtons. That's what we specify from our table of nodal applied loads. And that just means that for the rows of the force vector that correspond to node number 4, we will add the contribution of that nodal load directly into that component. And with that, this is a very brief overview, but it contains everything that you need to know about the direct stiffness method, which we will be applying to different types of equations. Next up is just applying this to the beam equation, or to the beam column element, so that you can analyze frames and mix. Then you can start mixing frames and trusses, and then we'll move on into continuum elasticity elements that we'll develop. But irrespective of what the problem is, the form of the direct stiffness method remains the same, is always the same. Form the local stiffness of the element, figure out what rows and columns belong to this element of the global system, and then add the corresponding contributions to the global stiffness and right-hand side. And that's it. And with that, we move on to our next chapter. Thank you.